5.2, I broke it into two parts in the notes. The first part is just sort of the understanding the theory behind linear programming and solving applications with corner points. And then the second part is just practicing it, putting it into practice. First case we're going to look at is the simplest case where they're bounded. In the second case, we're going to look at the case where it's unbounded and then practice both of them in 5.2 part 2. Alright, so 5.2 is a fairly big section, although the concept is basically the same and it's just putting it into practice in a couple different cases. Alright, so solving applications where we're restricted in a system of linear inequalities. So in chapter 3, we solved applications where we had a system of linear equations, which, we set those up and we could solve using a matrix. So this is going to be upping the ante here, where again those cases were either one solution, no solution, or infinitely many. With these, we have the inequalities, where we not only get the lines where they intersect, but also the shaded areas, or in our case, the unshaded areas. And this allows for more solutions. And a lot of these outcomes will have many solutions. Some of them will have infinitely many solutions. And so we're going to look at those. And then we're going to look at a special case of linear program where we actually want to use the solutions possible to optimize. Optimizing, we always want to optimize stuff, right? We always want to find either maximum values or minimum values. And we're going to stick to our cost, revenue, profit types. We want to maximize profit, minimize cost, and those types of things when we get to these applications. So again, these applications are commonly called linear programming. And the reason why it is because they're linear equations that we'll solve the system of. And there are programs that do this, that allow us to do this. Graphing is what we're going to come out, which you could graph with the graphing calculator, and I talked about that at the end of 5.1. I'm going to do them by hand, but again, feel free if you want to go through and check my answers graphically, you can do that graphically. I actually think it's easiest by hand, but to each their own. Alright, so first, setting it up. That's the hardest region. Just like with the solving systems when in chapter 3, the matrix part was easy. You plug it in the calculator does the algebra, gives you the answer. The hard part was the setup. Same thing's kind of true for these linear programming cases. The hard part typically for students is the setup. Now, these are a little more complex because we shade one half of the line, and you do have to figure that out. But again, usually students understand that it's the setup that's the more difficult part. So I'm going to look at an example, and right now we're going to stick with the bounded cases because those are the easier cases. In the next part, 5.2 part 2, we'll get into the unbounded cases. Alright, so an example of a linear programming type. And again, I'm going to walk you through it. So we've got Tom. He plans to start a business called River Explorers, and he wants to rent canoes and kayaks to tourists to travel down a river. He can spend up to $45,000. So he either has a loan, or he's saved this money, or inherited, or whatever. But his budget is $45,000 for boat purchases. All right, that's his budget. That's his limit there. He can spend up to that amount, but not over it. But he could technically spend less than it, right? If he spent less than it, means he's saving some money and he could spend it elsewhere in the business. And so he could spend up to $4,500, so that's again going to be an inequality. This is going to be less than that or equal to that. He's going to spend it on boats. All right, so there's the two types of boats. There's the canoe. Each of those costs $600. There's the kayak. Each of those costs $750. His facility, where he's going to hold the boats, can hold at most 65, meaning he can have up to 65 boats or fewer. Right? He doesn't have to have the capacity. And so that's what that at most means. 65 boats or less. And so there's a less than. The canoes he'll rent for $25 a day. The kayaks he'll rent, because kayaks are more expensive, so he's going to rent them for a slightly higher price of $30 per day. How many canoes and kayaks should he buy to earn the most revenue, right? We want to maximize revenue. Assume all boats will be rented daily, all right? And we're going to optimize. And that is a fairly large assumption, but we have to do that in order to solve the problem. All right, like I said, sometimes the hardest thing is the setup, not actually solving it. So I'm going to walk you through setting this up. All right, clearly you should know what your variables are, hopefully. All right, it's usually what you're doing. All right, we're going to buy a kayaks, buy canoes. All right, so X is going to represent the number of canoes he's going to buy. Y is going to represent the number of kayaks he's going to buy, right? That's what we're looking into. How many of those can we buy? And so your variables are always what you're trying to solve for. What do I need to find? All right, X's and Y's are always what we're trying to find. Write the constraint inequality. So these are the limiting values. That's what the constraint means. Constraint means there aren't infinitely many outcomes. I have a limit to how many outcomes I could have. And it's not equal to a certain amount. It's an inequality. So when we did systems of equations, they were constraints, but they were an equal to case. Right? When we did in chapter 3, the constraints were exact, right? And we wanted our totals to be exactly this. In these examples, we don't have to be exactly that amount. We could be either less than that amount or more than that amount, depending on how the problem's worded. And so I'm going to go through it, each line in the problem, kind of step by step, how we get these inequalities. So the first one comes from his budget. He can spend up to $45,000. That's his budget for buying boats. No more than that, but he could spend less than that. That's the difference between this and what we did in chapter 3. All right? He's going to spend it on his canoes and his kayaks, and the canoes are worth $600, the kayaks are worth $700. And so the starting is a lot like the equation we would have done in chapter 3. X represents canoes, so I have X of them. Each of them are valued at $600. So again, that's this part. Y's are kayaks. Each of them are valued at $750, and there's that. And this is the budget, which again, our inequality up to that amount, meaning you could spend less than it, right? It's just up to that. I can't go over it. So there's the equal to. I can spend $45,000, or technically he could spend less than his budget. He could save some money and use it elsewhere. Right? And so that's the equation from this particular set of, or this particular sentence in the application. Now, often, because we're going to be graphing these, we can't, you could leave it, and again, it's not wrong to leave it, but mathematicians tend to try to do things in the simplest way possible. And so in some cases, you'll see what we'll do is, well, I noticed that each of those are really big numbers, and I can reduce it. And so I chose to reduce it. I did that by dividing everything by 150. And again, this is an optional thing. You don't have to do it. It just makes, I'm going to go graph this and we're going to deal with the graph. It makes the graph a little easier and a little more manageable. That's the only reason we do it. And since I am going to use this example as my theory behind a very important theorem we're going to deal with, I am going to use the reduced form. So this is an example of where we started out with this. I divided everything by 150. And I reduced it down to a slightly more manageable one I can graph a little easier. Again, you don't have to do that. It's just something that we like to do so we can make it a little more, the numbers come out a little nicer when I go to graph. Alright, so those two equations are exactly the same. This is just the reduced form. The 4x plus 5y less than or equal to 300 still means the same thing. Still means budget of 4,500. X still represents the number of canoes. Y still represents the number of kayaks. It still follows the same pattern. Alright, so there's my first inequality. Like I said, I'm going to use the reduced form. So that's the first one. 4x plus 5y less than or equal to 300. The next one comes from how many boats he can use, right? He can only have as many boats that he can store, right? He doesn't want boats all over the place, right? There's probably there's probably some type of code that he has to follow. He can only have up to 65 boats. At most means he could have 65 boats or fewer. He doesn't have to have full capacity. But that would be the maximum, right? You can't go beyond 65. You could buy 65 boats or fewer. And so there's our inequality. So we get our 65 boats. So X represents the canoes, Y represents the kayaks. The sum of those boats, the canoes and kayaks, can be up to 65, which is the equal to part, or less than 65. I can't go over it. And so there's my second equation. Alright, and those are the two equations. Those are our two restrictions. Right, our two restrictions are our budget and how many canoes we can hold. Now, if you remember, I kind of talked about this a little bit in 5.1. Application problems, we should always stick to what makes sense, right? Those two lines actually shoot off into the negative direction. If I graphed them, a part of it would shoot off to negative infinity in both cases. They have arrows that would be shooting off negative. Well, I can't have negative values. I'm talking about canoes, right? And so for most applications, there's what these are called implied inequalities, where I have to only have, my answers can only consist of positive numbers. And so we always add these to our application cases. Canoes have to be positive, so x has to be bigger than or equal to 0. kayaks have to be positive. And they could be 0. You could buy no kayaks or could buy no canoes. You could just do all kayaks or all canoes. And so 0 is included, but we can't go negative because a negative canoe makes no sense. And for application types, those are always going to be implied inequalities are always going to be a part of it. So when we go to graph, we always graph in the first quadrant where the x and y values are positive. Always get rid of those negative x values, negative y values. All right, and so those are always, I say happens a lot. There's some cases where it doesn't, and I'm going to look at one example when I set it up. There's actually a little more involved than just this. But I'd say 98% of the time, you're always going to put those restrictions on your applications, those inequalities. All right, so we have the following system of what we call constraint inequalities. Constraint means this is what's limiting us, right? We're not allowed to go beyond these values, so they're a limit to us for this application. All right, so we've got our first equation, which represents the budget. The 4x plus 5y less than or equal to 300 is the same equation as the budget equation. The x plus y less than or equal to 65 is the total number of boats that we can have or fewer. And then the last two are our implied inequalities because we can only have positive numbers. All right, and again, that means first quadrant when I go to graph. So that's the inequality system. Right. Then the second part is the objective, what we want to do. We want to optimize, right? We want to find max and min values. And so when we want to optimize, well, we have to set up that equation. We want to, in this case, they're asking us to maximize revenue. And that comes from that last line in the paragraph. All right, a canoe can be rented for $25 a day. A kayak can be rented for $30 a day. How many canoes and kayaks should he buy to earn the most revenue? So there's asking us for a maximum. And so we set it up. We want to maximize our, so let capital R be my revenue. And so revenue generated. Remember, this is exactly the same revenue that we had in chapter 1, but we have two parts to it. There's the revenue generated from the X items, and there's revenue generated from the Y items. So remember, revenue is price times quantity, and that's true in this case. This is the price times quantity for canoes. This is the price times quantity for kayaks. So it is the same revenue. There's just two revenues because there's two values that I'm selling. So 25x represents the revenue for canoes, price of canoe times number of canoes, and 30y is the revenue for kayaks, price of kayaks times number of kayaks. And that's what we want to optimize. We want to find the solution within our constraints in order to maximize that equation, that revenue equation. All right, and we're going to get into sort of the theory behind this in the next set. So we'll get to now we'll solve the problem in the next video. So that was the setup, and sometimes the setup's the hard part. So there's the setup. The next video is going to be sort of the theory, and if you want to skip it, it's probably one of those videos you could skip. If you're curious as to why things pan out the way they do or the answer to this solution, that's in the next video. All right, so we'll stop this one here, and I'll pick up the how to solve it and what we get and sort of the theory behind what we're going to do in linear programming in the next video.